Explaining Bayes in 15 minutes is a bit of a tall order, but I'm going to have a go. The reason is that it's such an important and powerful utility that we have available these days, particularly in data mining technologies. But Bayes can be used outside of data mining technologies to analyze situations where uncertainty is present. The idea behind Bayes is very, very simple. In fact, if you simply say to someone, today the temperature is 0 degrees, they will immediately have in their mind, or possibly have in their mind, snow-covered fields or snow-covered buildings. You've narrowed down for them the possibility of what might be happening where you are. And this is the way Bayes works. Information is provided, and this information then determines the probabilities of whatever question it is that you're trying to resolve. Now, Bayes is used in many areas of life, in fact probably every area of life just about. It's certainly used in business, and I'm going to show a small, as simple as I could make it anyway, example of how to use Bayes. The reasons for focusing on Bayes in this particular video is that it can challenge some of our best held beliefs, our most treasured beliefs. Certainly Bayes has thrown light on doctors over-diagnosing, for example, and Bayes also throws light on overconfidence in business. You'll see that no matter how good you think your decision skills are, there are anomalies that pop out that may well be quite shocking. It's a rigorous method of incorporating information into the decisions that people make. And on the one hand, you have very highly mathematical treatments of the topic. On the other hand, you can have pragmatic, really quite subjective ways of using Bayes' theorem. Obviously, I'm not going to get through all of it in 15 minutes, but hopefully it'll give you a taste of how it's used. The core idea behind Bayes, and I've already alluded to it, is the specification of conditions. I've used the example here of weather. That blue area might contain all the samples of measurements that you've made over the past year or two on the weather. And we might be interested in the measurements that come under the category of cold and the measurements that come under the category of snow. Obviously there's going to be some overlap, as there is in that diagram. And as soon as we say it's cold, then we can look at that and we can say, well, actually there's a fairly good probability that it's going to be snowing as well. In fact, if you look at that diagram, as soon as we say it's cold, we can ignore everything else. Cold becomes our universe. And we then look at the overlap area with snow, and we can say, well, if it's cold, there's probably about a 30% chance of snow. Interestingly enough, it doesn't work exactly that way the other way around, because if we say it's snowing, then the overlap with cold is about, well, probably about 70%. So the two aren't symmetrical. This conditional probability is expressed by a statement. You can see here, probability of snow given that it is cold. That's what the vertical bar is, given that. This can be expressed mathematically more generally as the probability of A given B equals the probability of A and B. Mathematicians would express that as A intersect B, but let's keep it in plain English. So probability of A and B over the probability of B, because B is now our world. We've specified that event B has happened. So let's have a look at a problem that relates to making decisions in business. Imagine you work for a very, very smart organization. 90% of the projects presented to the board are winners. The people in your organization are very, very good at doing their job, and they won't take anything to the board unless they're 9/10 sure that it's going to be a winner. The board in turn are 90% accurate at picking out the winners and losers. So out of 100 projects, 90 that go to them will be winners, 10 will be losers, and the board is very good at picking out which are the winners and which are the losers. Also, we would think that with those kind of capabilities that there would be very few mistakes made, but actually it's not the case. This is a very busy slide. I shall go through it to the detail that is necessary to reach the conclusion that I need to. It won't be rigorous because it would just take too long. But S here represents, this is a tree obviously, S represents a successful project, U represents an unsuccessful project, P represents that it is passed by the board, R represents that it is rejected by the board. So 90% chance of getting a successful project, 90% chance of the board passing that project because they get it right 90% of the time, and a 10% chance of them rejecting it because they get it wrong 10% of the time. Similarly, 10% chance of an unsuccessful project, that is rejected 90% of the time because the board gets it right 90% of the time. 90% of the time they see that a particular project is going to be a failure. And 10% of the time they get it wrong, so they pass it. So here are the probabilities. You can work through, stop the slide, have a look at those if you want to. These are the conditional probabilities. So for example, the probability of the board passing a project given that it is successful is going to be 0.9, which is this thing here. It's a conditional probability. And the others are same for these other branches of the arms. So let's ask the question, what is the probability that rejected projects are projects that would have been unsuccessful? In other words, how accurate is the board at rejecting unsuccessful projects? So we go back a few slides maybe if you remember. The probability of a project being unsuccessful if it's been rejected, because rejected projects are now our universe. We're only interested in rejected projects. So what's the probability of it being unsuccessful if it's been rejected? Equals this. You can go back a few slides if you want to refresh on that. The probability of it being unsuccessful and rejected, we simply follow one of these arms. So it's this arm that's unsuccessful and rejected. So it's 0.1 times 0.9, which is 0.09. The probability of it being rejected, well, there's two ways it can be rejected. It can be rejected even though it's going to be successful, or it can be rejected because it's going to be unsuccessful. So we multiply those arms together, so 0.9 times 0.1 plus 0.1 times 0.9 gives us the probability of a project being rejected. So we then divide this term by this one here, and we get 50%. Shock horror. We'd be equally accurate as if we were flipping a coin. The probability of correctly categorizing an unsuccessful project is, to all intents and purposes, random. So that's not really a very good outcome, despite these superhuman capabilities of the management team and board in this particular organization. And this problem materializes over and over again in many different areas of life. In the law, in medicine, in warfare, in a whole raft of human activities. So that surprised me. I imagine it might surprise you as well. There are things that can be done to reduce these sort of errors, but that would take another 15 minutes. So maybe another slide. Sorry, another presentation. Bayesian methods are very widely used in data mining. They have the benefit that you can have many attributes. So, you know, if you're describing a situation, you could have, you know, maybe 50, 100, 1,000, whatever attributes, and you don't get killed by what is called the dimensionality problem. But anyway, to bring it back down to earth, this is a supervised learning method. You provide the algorithms with a whole pile of data. They learn to categorize, and then when you present new data, they will give you probabilities on which are the most likely categories for that data. So you might want to know whether a patient is ill or whether a patient is well, and if you have a database of information, you might be able to determine those things. Bayes, in actual fact, is very often overlooked for more esoteric methods, but actually it's a really good ground floor method. Naive Bayes is usually the method used. It assumes that the attributes are independent of each other. Very often they're not. So, for example, if you had an attribute of temperature and precipitation, it may well be that those are not independent. But at the end of the day, good results are very often got, even though independence isn't a part of the attributes or part of their properties. Here's Bayes' rule in all its glory for those who like this kind of thing. It's very, very simple, really. All you need is a partition and an event, and you have Bayes' rule. And the partition is just a way of dividing up your sample space, your universe of data, in a way where the areas don't overlap. But there's a formula. So that's a very brief overview of Bayes' rule. It's used everywhere. It's certainly used in most disciplines. No reason why it shouldn't be used in business on a routine basis. And I think I'll probably end up producing another presentation on its use in data mining specifically. Anyway, thank you for your time.